Hello there, and welcome to Sleepy Science. Right now, something invisible is passing through your body and the entire Earth. We can't see it or detect it directly, but the universe behaves as if it's everywhere. When astronomers study galaxies, the gravity they observe is far stronger than visible matter can explain. In fact, about 85% of the universe's matter appears to be invisible. Scientists call this mysterious substance dark matter, and without it, galaxies like our Milky Way might not even exist. If the universe is full of stars, planets, and bright galaxies, then a simple question appears. Why do astronomers say that most of the universe is missing? When scientists study space, they measure how objects move. They also calculate how much gravity is needed to control that motion. When they compare the numbers, something strange appears. The visible objects in space do not seem heavy enough. The stars, gas, and planets we can see only explain a small part of the gravity that exists. The rest seems to come from something invisible. It is like looking at a spinning wheel and realizing the center must be much heavier than it looks. Astronomers did not expect this result at all. For many years, they believed they understood what filled the universe. But careful measurements kept giving the same strange answer. Something large and unseen seemed to be affecting everything. So the big mystery slowly appeared. If we can see so many stars and galaxies, why does the math say most of the matter is missing? When astronomers measure how galaxies move, they use gravity to explain the motion. Gravity is the force that pulls objects toward each other. It keeps planets around stars and stars inside galaxies. Normally, the amount of gravity depends on how much matter is present. More matter means stronger gravity. But when scientists observe galaxies, the gravity seems too strong. The stars move as if a huge amount of hidden mass is present. The visible stars and gas do not provide enough gravity to explain what is happening. Imagine watching cars move around a track much faster than expected. You would assume something unseen is pushing them. Astronomers faced a similar puzzle in space. The universe behaves as if there is far more matter than we can see. The extra gravity seems to surround galaxies like an invisible structure. This strange behavior forced scientists to question their understanding of the universe. If the gravity is real, then something unseen must be creating it. In the early days of astronomy, scientists believed they understood what filled the universe. They assumed that all matter in space came from normal things like stars, planets, gas clouds, and dust. These were objects that telescopes could see or detect. When astronomers looked at galaxies, they counted the stars and estimated how much mass they contained. They believed this visible matter explained the gravity inside galaxies. The idea seemed reasonable at the time. After all, everything we know on Earth is made of ordinary matter. Rocks, water, air, and people all follow the same basic rules. So scientists expected the universe to work the same way. If something created gravity, it must be made of normal atoms. For many years this assumption guided research. But as telescopes improved, astronomers began collecting more accurate data. The more they studied galaxies, the more small problems appeared. The numbers slowly stopped matching expectations. That raised a quiet but important question. Could the universe contain something other than ordinary matter? The first strong hints of a problem came when astronomers carefully studied how galaxies move. A galaxy contains billions of stars that travel around its center because of gravity. Scientists expected stars near the center to move faster. Stars farther away should move more slowly because they feel less gravitational pull. This idea works well in many systems, including planets around a star. But when astronomers measured the motion of stars in galaxies, the results were surprising. Stars far from the center were moving much faster than expected. In some cases, they moved almost as fast as stars close to the middle. According to the known laws of gravity, this should not happen. The outer stars should have slowed down. Instead, they kept moving quickly as if a large amount of hidden mass surrounded the galaxy. This discovery made scientists pause and think carefully. If the stars were not slowing down, something else must be creating extra gravity. But what exactly was hiding there? In the 1930s, a Swiss astronomer named Fritz Zwicky began studying large groups of galaxies. One group caught his attention. It was called the Coma Cluster. A galaxy cluster is a huge collection of hundreds or even thousands of galaxies held together by gravity. Zwicky wanted to understand how these galaxies moved inside the cluster. Using powerful telescopes and careful calculations, he measured their speeds. At first, this seemed like a normal research project. Astronomers often study motion to estimate how much mass exists in space. But as Zwicky looked closer at the data, something strange appeared. The galaxies inside the cluster were moving extremely fast, much faster than scientists expected. This raised an important question. What kind of gravity was strong enough to keep such fast galaxies together? Zwicky realized that this cluster might reveal something new about the universe. What he discovered next would become one of the earliest clues in the mystery of dark matter. When Zwicky measured the motion of galaxies inside the Coma cluster, he saw speeds that did not make sense. The galaxies were moving very quickly around the center of the cluster. Normally, objects moving that fast should escape the cluster's gravity. Imagine throwing a ball upward with enough speed. If it moves fast enough, it will escape Earth's gravity and never fall back. The same idea works in space. If galaxies move too fast, they should fly away from the cluster. But that was not happening. The galaxies in the Coma cluster were staying together. They were still trapped by gravity. This created a strange puzzle for Zwicky. According to the laws of physics, something must be providing enough gravitational pull to hold the cluster together. But when he counted all the visible matter, the numbers did not match the observed speeds. The galaxies seemed to be moving far too quickly for the amount of visible mass present. Zwicky then tried to solve the puzzle using the matter he could see. He estimated the total mass of all the galaxies in the cluster. This included the stars, gas, and dust inside them. After calculating everything, he compared the mass to the speeds of the galaxies. The result was surprising. The visible matter was far too small to create the gravity needed. If the cluster only contained the stars and gas that telescopes could observe, the galaxies should not stay together. They should have escaped the cluster long ago. Yet the cluster remained stable. The galaxies continued moving inside it as if something powerful was holding them. This left Zwicky with a very unusual conclusion. The cluster seemed to contain much more mass than anyone could see. Something hidden had to be adding extra gravity. But what could it be? At the time, no telescope had ever detected such invisible matter. After studying the data carefully, Zwicky reached a bold conclusion. He suggested that a large amount of hidden mass existed inside the cluster. This invisible matter must be creating the extra gravity that keeps the galaxies together. Without it, the cluster would slowly fall apart. Zwicky called this unseen material dunkle materie, which means dark matter. His idea was simple but surprising. He believed the universe might contain matter that does not produce light and cannot be seen with telescopes. This hidden mass would still create gravity, even though it remains invisible. At first, many scientists were unsure about his claim. The idea sounded strange and difficult to prove, but Zwicky's calculations were clear. The galaxies in the Coma cluster behaved as if a huge amount of unseen matter surrounded them. His work planted the first strong seed of a new mystery. Could most of the universe be made of something invisible? After studying the strange motion of galaxies in the Coma cluster, Fritz Zwicky proposed a bold explanation. He believed that a large amount of unseen matter must exist in space. This hidden matter was not producing light, so telescopes could not see it, but it still created gravity. Zwicky gave this mysterious substance a name. He called it Dunkelmaterei, a German phrase that means dark matter. The idea was simple but powerful. If extra invisible matter filled galaxy clusters, it could explain why galaxies stayed together even when moving very fast. According to his calculations, the hidden mass was far larger than the visible mass. That meant most of the matter in that cluster could not be seen at all. This suggestion sounded unusual at the time. Astronomers were used to studying objects they could observe with telescopes. Now Zwicky was suggesting that the universe might contain a huge amount of matter that no one had ever directly detected. Even though Zwicky's idea was interesting, many scientists did not accept it right away. In fact, for several decades, the idea received little attention. One reason was the lack of strong evidence. Zwicky had studied one galaxy cluster, but astronomers wanted to see the same pattern in many places. Science usually moves slowly when a new idea appears. Researchers prefer to collect more observations before changing their understanding of the universe. Another reason was that dark matter sounded very unusual. The idea suggested that most of the universe might be made of something invisible. At that time, telescopes were not advanced enough to explore this mystery deeply. So many astronomers continued focusing on visible objects like stars and gas clouds. Zwicky's work remained in the background for many years, but the question he raised did not disappear. Quietly, the universe continued behaving in strange ways that scientists would later notice again. Several decades later, the mystery returned in a new way. In the 1970s, an American astronomer named Vera Rubin began carefully studying how galaxies rotate. She worked with powerful telescopes that could measure the motion of stars inside galaxies. Her goal was simple. She wanted to understand how stars move around the centers of galaxies. Every galaxy contains billions of stars held together by gravity. Just like planets move around a star, these stars travel around the center of the galaxy. By measuring their speeds, Rubin hoped to estimate how much mass existed inside galaxies. At first, this seemed like a routine scientific project. Astronomers had studied galaxy motion before, but Rubin's measurements were more precise than earlier observations. When she started collecting data, the results revealed something unexpected. The motion of stars inside galaxies did not behave the way scientists predicted. This discovery would soon reopen the strange mystery first noticed decades earlier. Before Rubin's measurements, astronomers had a clear expectation about how stars should move in a galaxy. The idea came from the basic rules of gravity. When objects orbit around a center, the inner ones usually move faster. The outer ones move slower because they are farther from the strongest pull of gravity. A simple example exists in our own solar system. Planets closer to the sun travel around it more quickly. Planets farther away move more slowly because the sun's gravitational pull is weaker at greater distances. Astronomers expected galaxies to behave in a similar way. Stars near the center of a galaxy should move very fast. Stars near the outer edges should move more slowly. This pattern seemed logical and matched the known laws of physics. So when scientists began measuring galaxy rotation, they expected to see this gradual slowdown. But as new observations appeared, something surprising began to challenge that expectation. To understand what astronomers expected, it helps to look at our own solar system. Planets move around the sun because of gravity. The closer a planet is to the Sun, the stronger the pull of gravity. Because of this strong pull, inner planets move faster in their orbits. Mercury, for example, travels around the Sun very quickly. It completes an orbit in only about 88 days. Planets farther away behave differently. Jupiter and Saturn move much more slowly because they are farther from the Sun's strongest gravity. This pattern is simple and predictable. Stronger gravity near the center means faster motion. Weaker gravity farther away means slower motion. Astronomers expected galaxies to follow the same rule. The center of a galaxy contains most of its visible stars. That means the strongest gravity should be near the center. So stars far away from the center were expected to move more slowly. This idea seemed completely reasonable before careful measurements began. When Vera Rubin began studying galaxy rotation in detail, she focused on a nearby galaxy called the Andromeda Galaxy. This galaxy is one of the closest large galaxies to our own Milky Way. Because it is relatively close, astronomers can observe its stars more clearly. Rubin used sensitive instruments to measure how fast different stars were moving as they orbited the galaxy's center. At first, she expected the data to follow the usual pattern. Stars near the center should move quickly. Stars far from the center should slow down. But when Rubin carefully analyzed the results, the pattern looked very different. Instead of slowing down, the stars at larger distances kept moving at high speeds. The outer parts of the galaxy behaved in a way that did not match the predictions of normal gravity using only visible matter. This unexpected result made Rubin look even more closely at her measurements. Rubin continued measuring stars at different distances from the center of the Andromeda Galaxy. What she found was consistent across the galaxy. The stars far from the center were moving almost just as fast as the stars closer to the middle. Instead of slowing down, their speed stayed nearly constant. This was surprising because the visible mass of the galaxy becomes thinner toward the edges. There are fewer stars and less gas in those outer areas. According to normal expectations, less mass should mean weaker gravity, and weaker gravity should lead to slower motion. But the observations did not show that pattern. The outer stars kept moving quickly as if a strong gravitational pull still existed there. Rubin repeated similar measurements with other galaxies. Again and again, the same strange pattern appeared. The outer stars refused to slow down. This raised an important question. What was creating the extra gravity in the outer parts of galaxies? This strange motion created a serious problem for astronomers. If only the visible matter existed in the galaxy, the outer stars were moving far too fast. Gravity from the known stars and gas should not be strong enough to hold them in orbit. When objects move quickly in space, they can escape the gravitational pull of the system they belong to. A good example is a rocket leaving Earth. If it reaches a high enough speed, Earth's gravity can no longer pull it back. The same rule applies to stars inside galaxies. If they move too fast, they should fly away into space. But that was not happening in the Andromeda Galaxy. The outer stars remained in their paths around the center. This meant some extra gravitational force must be present. Something unseen had to be adding mass to the galaxy. Without that extra mass, the galaxy should slowly fall apart over time. The puzzling motion of stars and galaxies left astronomers searching for answers. One idea quickly became the most logical explanation. If the visible matter in a galaxy was not enough to create the gravity needed, then there must be additional matter that we cannot see. This invisible mass would surround the galaxy in all directions, forming a kind of protective envelope. It would act as an unseen weight holding the stars in place, especially those at the outer edges moving faster than expected. Scientists realized that this massive, invisible structure must exist because there was no other explanation that fit the observations. Without it, galaxies like Andromeda or the Milky Way would not be able to stay intact. The outer stars would simply escape into space over millions of years. The idea of an unseen, gravitational force surrounding galaxies became the foundation for understanding why galaxies remain stable even when much of their mass cannot be observed directly. It was a silent, invisible presence shaping the universe. Scientists gave this invisible structure a name, a dark matter halo. Unlike the stars, gas, or dust that we can see with telescopes, this halo does not emit, reflect, or absorb light. It is entirely invisible to ordinary observation, yet its gravitational influence is enormous. The halo provides the extra pull needed to keep all the stars moving along their orbits safely. It acts as a hidden skeleton for the galaxy, giving structure and stability. Every galaxy, including our own Milky Way, is believed to sit inside such a halo. These halos can be several times larger than the galaxy's visible part, meaning the stars we see are just the inner layer. The idea of a dark matter halo helped astronomers understand many strange observations. It explained why the outer stars move so quickly and why galaxies do not tear apart. The halo is a key piece of the cosmic puzzle. These halos are not small. They extend far beyond the visible edges of galaxies. The stars and gas that we can see form only a small fraction of the total mass. Beyond them, the dark matter halo continues outward for hundreds of thousands or even millions of light years. This means that the galaxy is much larger than it appears through a telescope. The visible part is just the tip of the iceberg. The majority of the galaxy's mass lies in this invisible envelope. It creates gravity that affects the motion of stars, satellite galaxies, and even intergalactic gas. Dark matter halos connect galaxies to the larger structures of the universe. Without them, galaxies would not have formed the way they did. These vast, invisible halos remind us that most of the universe is hidden from our eyes, even though it shapes everything we can see. Because of these halos, our understanding of galaxies had to change. A galaxy is not just the stars, planets, and gas we observe. It is an enormous system held together by an unseen mass surrounding it. This changes the way we imagine the size and structure of galaxies. What we see is only the bright center, while the dark matter halo forms a massive, invisible boundary. It stretches far into space and affects how galaxies interact with each other. These halos also influence galaxy collisions, star formation, and the growth of cosmic structures. They are not just passive containers. They are active players in the evolution of the universe. By studying the behavior of stars and gas, astronomers can map these halos and learn about the unseen majority of a galaxy's mass. It is as if the visible galaxy floats inside a hidden sea of dark matter, shaping its destiny and keeping it whole. As astronomers studied galaxies and their halos more carefully, a surprising realization emerged. Dark matter is not just a small part of galaxies. It may actually dominate the mass of the entire universe. Every galaxy, every cluster of galaxies, seems to be influenced more by invisible matter than by the stars and gas we can see. When scientists added up the estimated mass of all galaxies, clusters, and the space between them, the majority of that mass could not be accounted for by ordinary matter. It became clear that the universe is not mostly made of the matter we are familiar with. Instead, the invisible dark matter plays the leading role in shaping galaxies, their motion, and the large-scale structure of the cosmos. This realization completely changed the way astronomers think about the universe. What we see is only a tiny fraction of what is really out there. Dark matter is the hidden framework holding the cosmos together, quietly shaping everything on the largest scales. When scientists calculated the contribution of visible matter to the universe's total mass, the results were striking. Stars, planets, gas clouds, and dust account for only a very small fraction of what is needed to explain the gravitational forces observed across galaxies and clusters. Most of the universe's matter does not emit light and cannot be seen with any telescope. Even massive clusters that contain thousands of galaxies show that visible matter alone is insufficient. Ordinary atoms make up only a few percent of the total cosmic mass. Everything else, the majority of the mass, seems invisible. This invisible matter is not just hiding in one galaxy or one cluster. It appears to be everywhere. From the largest galaxy clusters to the space surrounding individual stars, dark matter seems to dominate the universe. Scientists had to accept a new reality. The visible universe is only the tip of the iceberg. The rest is hidden, yet it governs the behavior of galaxies and cosmic structures. Through careful measurements and modeling, astronomers began estimating the proportion of dark matter in the universe. The results were astonishing. Roughly 85% of all matter in the universe appears to be dark matter. That means the stars, gas, and planets that we can observe make up only about 15% of the total matter. Most of the mass in the cosmos is invisible, yet it shapes everything we see. Galaxy rotation curves, gravitational lensing, and cluster dynamics all point to this conclusion. Dark matter is not confined to special locations. It is spread throughout galaxies and clusters, forming halos, webs, and filaments. Its presence affects the motion of stars, the growth of galaxies, and the formation of cosmic structures. Without this invisible majority, the universe would look completely different. Its gravitational influence is the reason galaxies stay intact and why large-scale structures exist. The dominance of dark matter is one of the most striking facts in modern astronomy. If dark matter is so common, spread across galaxies and clusters, a natural question arises. Why can't we see it? Why is it completely invisible? Unlike stars or gas, dark matter does not emit light, absorb it, or reflect it. Telescopes cannot detect it directly. It is not hot or bright, and it does not produce radiation we can measure easily. Its presence is only revealed through its gravitational effects. Stars, gas clouds, and even entire galaxies respond to the unseen pull of dark matter. Yet billions of years of study have not revealed any direct evidence of its nature. This question challenges scientists and sparks curiosity. How can something so massive and influential remain hidden? And if it is everywhere, including inside our own Milky Way, what does that mean for our understanding of the universe? The mystery of dark matter is not just a puzzle. It is a central feature of the cosmos we live in. One of the strangest properties of dark matter is that it does not interact with light in any way. Light is what allows us to see stars, planets, and galaxies. When light hits an object, it can reflect, scatter, or pass through. Normal matter responds to light, which is why telescopes can detect it. Dark matter, however, is completely different. It seems invisible to all forms of light, including the kinds we cannot see, like infrared or ultraviolet. This lack of interaction is what makes it so mysterious. It does not glow, shine, or create shadows. Even though it has mass, it behaves in ways that ordinary matter does not. Scientists call it dark because it cannot be observed through conventional methods. The fact that dark matter does not interact with light is the main reason it remained hidden for so many decades. Its presence is only felt through its effects on the cosmos around it. Because dark matter does not interact with light, it cannot reflect, absorb, or emit it. This means it does not behave like stars or gas clouds. Stars shine because they produce light from nuclear reactions. Gas clouds can absorb and re-emit light, making them visible to telescopes. Planets reflect light from their stars, allowing us to see them. Dark matter, on the other hand, cannot be seen this way. Even if a galaxy contains a huge amount of dark matter, it will not produce any light of its own. Telescopes, no matter how powerful, cannot capture images of dark matter directly. This property makes it fundamentally different from anything humans have studied in space. It is invisible in every sense, yet it is massive and influential. The universe contains vast amounts of this unseen material, shaping everything from the motion of stars to the structure of galaxy clusters. Because of its invisibility, no telescope can detect dark matter directly. Observatories and space telescopes rely on light to observe distant objects. Stars, nebulae, and galaxies all shine or reflect light, making them visible. But dark matter remains completely hidden. Even when it passes through Earth, we cannot see or feel it. It does not block sunlight or interact with our instruments. This makes studying dark matter extremely challenging. Scientists cannot observe it in the same way they study other objects in space. Instead, they have to look for indirect clues. By measuring the motion of stars, galaxies, and clusters, astronomers can infer the presence of something massive that is invisible. Even without direct detection, its effects are undeniable. Dark matter shapes the cosmos silently, like an invisible skeleton holding galaxies together, while telescopes can only see the ordinary matter on top of it. Even though dark matter cannot be seen, its presence is revealed by gravity. Gravity is the force that pulls objects toward each other. Stars orbit the centers of galaxies because of the gravitational pull from visible and invisible matter. When stars move faster than expected, it shows that extra mass must exist. Galaxy clusters also act as evidence. The way galaxies move inside clusters cannot be explained by visible matter alone. Gravitational lensing provides another clue. When light from distant galaxies passes near massive objects, it bends. The amount of bending shows how much mass is present, even if it is invisible. Dark matter creates the extra gravity needed to explain these observations. Its effect is strong enough to shape the motion of stars, the formation of galaxies, and even the structure of the universe. While we cannot see it, we can see how the universe responds to its presence. One of the most powerful ways scientists study dark matter is through a phenomenon called gravitational lensing. This is a method that allows astronomers to map the presence of invisible matter by observing its effect on light. Even though dark matter cannot be seen directly, it still has mass, and mass affects the path of light. By carefully observing distant galaxies and the way their light is distorted as it travels toward us, scientists can create maps showing where dark matter exists. Gravitational lensing acts like a natural telescope, magnifying and bending light in ways that reveal hidden structures. Clusters of dark matter produce a stronger lens effect, making the light from objects behind them appear stretched, curved, or multiplied. By analyzing these distortions, astronomers can estimate the amount and distribution of dark matter in the universe. It is one of the most indirect yet convincing methods to see something that cannot be observed with ordinary light. Gravity does more than keep planets in orbit or hold stars together. According to Einstein's theory, gravity can actually bend light as it passes near massive objects. Light travels in straight lines, but when space itself is warped by mass, those straight lines appear to curve. The more massive an object, the more it bends the light passing nearby. This effect is not noticeable in everyday life, but becomes very strong near galaxies or clusters of galaxies. By studying these distortions, astronomers can measure how much mass is present, even if it is invisible. Gravitational lensing provides a way to see dark matter indirectly, because the visible stars alone cannot explain the observed bending. Light from distant objects acts like a tracer, revealing the hidden mass that surrounds galaxies. It is a natural tool that the universe provides, allowing scientists to map the unseen and understand the structure of the cosmos. Massive objects in space, such as stars, black holes, or galaxy clusters, do not just pull on nearby objects, they actually warp space itself. This idea comes from Einstein's theory of general relativity, which explains gravity as the bending of space and time by mass. Instead of thinking of gravity as an invisible force acting at a distance, relativity describes massive objects as creating curves in space. Light traveling through these curves changes direction, bending slightly as it passes. This explains why gravitational lensing works and why distant galaxies can appear distorted or multiplied. By measuring these distortions, scientists can estimate the mass that is causing them. The visible stars and gas are often not enough to create the observed warping. This extra mass is attributed to dark matter. General relativity gives scientists a framework to understand how invisible matter affects the universe around it. When dark matter gathers in large clusters around galaxies, it creates additional mass that bends light passing behind it. Light from more distant galaxies, traveling toward Earth, passes through regions filled with dark matter. As it moves through these regions, the path of the light is altered, creating arcs, curves, or multiple images of the same galaxy. These distortions are subtle, but sensitive instruments can detect them. By analyzing the degree of bending, astronomers can map the shape and amount of dark matter in the cluster. This technique reveals where dark matter is concentrated, even though it remains invisible. Gravitational lensing allows scientists to study the distribution of dark matter on a large scale, showing that it forms halos around galaxies and filaments between clusters. It provides a clear example of how invisible matter shapes the universe, influencing light and motion across billions of light years. When light from distant galaxies passes near massive objects like galaxy clusters, astronomers can see the effect in the images they capture. These images often appear stretched, curved, or even multiplied. The distortions are not random. They follow patterns that show the influence of gravity. By comparing the shapes of many background galaxies with what they should look like if space were empty, astronomers can detect where extra mass is pulling on the light. Even though the mass causing the bending cannot be seen, its effect is clear in the shapes of these distant galaxies. Each distorted image acts like a clue pointing to the hidden matter in space. By carefully measuring and analyzing these distortions, scientists can understand how much invisible mass exists and where it is located. Gravitational lensing provides one of the most convincing ways to study dark matter, showing its presence across billions of light years of space. By studying these distortions in detail, scientists can create maps showing the distribution of dark matter. These maps are not like ordinary pictures of stars or galaxies. Instead, they represent areas of space where invisible matter is concentrated. By using the bending of light as a guide, astronomers can trace the shape and size of dark matter halos around galaxies and clusters. The maps reveal patterns of gravity that cannot be explained by visible matter alone. These observations allow scientists to see how dark matter is spread across the universe, forming the framework on which galaxies are built. The process requires careful measurement and analysis, but the results are clear. Even though we cannot see dark matter directly, these maps reveal its invisible presence and its crucial role in shaping the cosmos. The patterns show that the universe is structured in ways far beyond what our eyes can detect. These dark matter maps reveal enormous structures in the universe that were invisible before. Clusters of dark matter appear as vast halos surrounding galaxies and groups of galaxies. These halos connect with each other through long filaments, forming immense structures spanning hundreds of millions of light years. The dark matter forms a kind of scaffolding, with galaxies gathered along the strands and clusters at intersections. Observations show that the universe is not uniform on large scales. Instead, it has a web-like structure where matter is concentrated in some regions and almost empty in others. This discovery has transformed our understanding of the cosmos. The visible galaxies we can see are only part of a much larger network shaped by dark matter. Without these invisible structures, galaxies might never have formed or remained stable. The maps give us a way to see the hidden framework that holds the universe together. This leads to the concept of the cosmic web. The cosmic web is the large-scale structure of the universe shaped by dark matter. It consists of long filaments of matter stretching across vast distances, connecting clusters of galaxies at their intersections. Most galaxies form along these filaments, following the gravitational pull of the invisible mass. Between the filaments, there are enormous voids where very little matter exists. The cosmic web shows that the universe has an organized, interconnected structure on the largest scales. Dark matter acts as the framework of this web, guiding where galaxies and clusters form. Studying the cosmic web helps astronomers understand the evolution of the universe and the role of dark matter in shaping it. It also reveals that the universe is far more vast and complex than it appears when we look only at stars and galaxies. Galaxies do not form randomly in space. Instead, they tend to appear along enormous filaments of dark matter. These filaments are invisible, yet they have mass and create gravitational pull. Gas and dust follow the pull of these invisible strands, slowly accumulating over billions of years. Stars form from this gas, and eventually entire galaxies take shape along the dark matter highways. The filaments act like invisible pathways guiding where galaxies will emerge. This explains why galaxies are not evenly spread across the universe. Most lie along these long, thread-like structures, leaving vast empty regions in between. Observations using gravitational lensing and galaxy surveys have confirmed this pattern. The connection between dark matter filaments and the visible universe shows how important dark matter is in shaping the cosmic landscape. Without these filaments, galaxies would likely have formed in a more scattered and less organized way. Dark matter quietly directs the flow of matter on cosmic scales. These dark matter filaments are enormous, stretching across hundreds of millions of light years. To put that into perspective, 1 light year is the distance light travels in a single year, nearly 6 trillion miles. Now imagine structures that are hundreds of millions of light years long. These filaments form the skeleton of the universe, invisible yet vast and powerful. Even though we cannot see them directly, their presence is traced by the galaxies that form along them and the gravitational effects they create. The scale of these filaments is hard to imagine. They connect galaxy clusters over unimaginable distances, creating a network that stretches across the observable universe. They are not small or isolated structures, but immense threads linking countless galaxies. Studying these filaments helps astronomers understand how the universe evolved from a nearly uniform state after the Big Bang into the complex cosmic web we see today. Galaxies do not just form along the filaments. They tend to gather at the intersections of these invisible strands. Where 2 or more filaments cross, gravity is stronger because the mass of dark matter is concentrated there. These intersections become hubs where galaxies cluster together, forming massive galaxy clusters and superclusters. These hubs are some of the most massive structures in the universe. The concentration of galaxies at filament intersections explains why the universe has dense regions separated by vast empty voids. Even though the filaments themselves are invisible, their intersections are revealed by the galaxies they hold together. This pattern repeats across the cosmos, showing a clear connection between the invisible dark matter and the visible universe. Without the dark matter filaments, these intersections and dense galaxy clusters would likely not exist in their observed form. The way galaxies follow filaments and gather at intersections suggests that dark matter acts like a cosmic scaffolding. Just like scaffolding supports the construction of a building, dark matter provides the framework that shapes the large-scale structure of the universe. Visible matter, gas, stars, and galaxies collects along this invisible support, forming the patterns we can see through telescopes. Without this scaffolding, matter might be spread thinly across space, preventing the formation of galaxies, clusters, or superclusters. Dark matter's gravitational pull ensures that structures grow and remain stable over billions of years. This scaffolding concept helps scientists understand why the universe has the web-like pattern of filaments and voids, and why galaxies appear in clusters rather than being scattered randomly. Essentially, dark matter is the hidden architecture upon which the universe is built, guiding matter into the shapes and structures that define the cosmos. Without dark matter, the universe would look very different. Galaxies might never have formed at all. Stars, gas, and dust need a gravitational framework to gather and condense. If there were only ordinary matter, these components would have spread out too thinly across space. Gravity from visible matter alone would not have been strong enough to pull material together into stars and galaxies. Dark matter provided the hidden mass that made this possible. Its gravity created regions where matter could collect and remain stable. Over time, these regions grew larger as more gas and dust fell into the gravitational wells created by dark matter. This process allowed the first galaxies to take shape, eventually forming the vast and structured universe we see today. Without dark matter acting as the invisible glue, galaxies might have failed to form, leaving a mostly empty universe with few or no stars. Its presence was essential for the cosmic structures we observe. The early universe was not perfectly uniform. Instead, it was filled with tiny density fluctuations, small variations in the distribution of matter. Some regions were slightly denser, while others were slightly emptier. These differences were very small at first, but they were crucial for the formation of cosmic structures. The fluctuations provided the seeds for galaxies and clusters. Gravity acts more strongly in regions with slightly higher density, pulling in nearby matter. Over time, these dense regions grew larger, while the emptier areas became voids. Without these initial fluctuations, matter would have remained spread evenly across space, and no large structures could have formed. The universe's complex pattern of filaments, clusters, and voids began with these tiny differences. Understanding these early variations helps scientists see how dark matter and gravity shaped the cosmos over billions of years. Dark matter played a critical role in amplifying these tiny fluctuations. Because it has mass and responds to gravity, it pulled matter toward the slightly denser regions in the early universe. Unlike ordinary matter, dark matter does not interact with light, so it started clumping earlier, even before gas could cool and form stars. As these clumps of dark matter grew, they created stronger gravitational wells that attracted more material. Gas and dust followed the invisible pull, eventually forming stars and galaxies inside these dark matter concentrations. This process accelerated the growth of cosmic structures, turning minor variations into the large-scale patterns we see today. Dark matter acted like an invisible accelerator, giving gravity the extra power needed to shape the universe. Without it, galaxies would have taken much longer to form if they formed at all. It provided the essential scaffolding for cosmic evolution. Over billions of years, this process allowed galaxies to grow and evolve. The initial dark matter clumps formed the centers around which visible matter could gather. Gas cooled and condensed, forming stars and star clusters within these gravitational wells. Over time, smaller structures merged, creating larger galaxies and galaxy clusters. Dark matter ensured that galaxies remained stable as they grew, holding stars and gas together despite their motion. The cosmic web continued to develop, with filaments and intersections forming the framework for galaxy distribution. Without the gravitational pull of dark matter, these growth processes would have been much slower or might not have occurred. Today, every galaxy, from small dwarfs to massive spirals like the Milky Way, owes its existence to this invisible mass. In essence, dark matter allowed the universe to transform from tiny fluctuations in the early cosmos into the vast, structured and beautiful system we observe today. Scientists today study galaxy formation not just by observing the universe, but also by using computer simulations. These simulations allow them to recreate how galaxies form and evolve over billions of years. Dark matter plays a central role in these models. By including dark matter, the simulations can show how gravity shapes the movement of gas, stars, and galaxies. Dark matter creates the invisible framework where ordinary matter can collect and form structures. Without it, the models struggle to reproduce the large-scale patterns seen in the real universe. Simulations help scientists test theories and understand how galaxies grow from the tiny density fluctuations in the early universe. They also allow researchers to experiment with different amounts and properties of dark matter to see what best matches the observed cosmos. In this way, computer models provide a virtual laboratory for understanding the invisible forces shaping the universe. When scientists try to run galaxy formation models without dark matter, the results are strikingly different from what we observe in space. Galaxies in these simulations are small, irregular, and often fall apart over time. There are no large clusters or well-formed structures. The motions of stars and gas do not match what astronomers see through telescopes. Without the gravitational pull of dark matter, galaxies cannot grow efficiently or maintain their shapes. Even when the initial conditions resemble the early universe, the resulting cosmic web and clusters fail to appear. This shows that ordinary matter alone cannot explain the large-scale structure of the cosmos. By comparing these failed simulations to reality, scientists gain strong evidence that something invisible must be providing extra mass and gravity. It becomes clear that dark matter is not just a theory. It is necessary to explain how galaxies actually form and evolve. When scientists include dark matter in their models, something remarkable happens. The simulations start to resemble the universe we observe today. Galaxies form along filaments of dark matter, clusters develop at intersections, and the cosmic web emerges naturally. The rotation speeds of stars within galaxies match the observed rotation curves. The motions of galaxy clusters and gravitational lensing effects also align with reality. This agreement is surprising because the models use only the known laws of physics and include dark matter as an invisible component. The fact that the simulations reproduce so many observed features strengthens the idea that dark matter exists. It provides a consistent explanation for the distribution of galaxies, the growth of structures, and the stability of cosmic systems over billions of years. Without dark matter, none of these results could be recreated so accurately. The success of these models gives astronomers strong confidence in the existence of dark matter. When independent observations, galaxy surveys, and gravitational lensing data all match the predictions from simulations that include dark matter, it provides compelling evidence that the invisible mass is real. Dark matter is not just a mathematical trick. It is a crucial ingredient that shapes the universe. Every well-formed galaxy, massive cluster, and filament in the cosmic web can be explained when dark matter is included. The consistency between simulations and observations strengthens scientists' understanding and shows that dark matter is a fundamental part of our cosmos. Even though it cannot be seen directly, its influence is everywhere, guiding the evolution of galaxies and forming the scaffolding upon which the universe is built. The agreement between theory, simulation, and observation makes dark matter one of the most important discoveries in modern astronomy. Despite all the evidence for dark matter, the biggest mystery remains. What is it actually made of? Scientists have confirmed that it exists because of its gravitational effects, but no one has ever seen a dark matter particle directly. It does not shine, absorb, or reflect light, and it does not behave like anything familiar in the universe. Researchers have proposed many ideas, from new types of particles to exotic forms of matter that have not yet been discovered. Some experiments attempt to detect these particles on Earth or observe their interactions in space. Others look for signs of dark matter decaying or annihilating in distant galaxies. Even after decades of study, the fundamental nature of dark matter remains unknown. This mystery keeps astronomers and physicists searching for answers. Every new experiment, telescope, or particle detector adds clues, but the true identity of dark matter continues to elude us, making it one of the most fascinating puzzles in science today. Scientists are certain that dark matter cannot be made of normal atoms. Atoms form everything we can see: stars, planets, gas, dust, and even our own bodies. Normal atoms interact with light, either emitting it, reflecting it, or absorbing it. They also respond to electromagnetic forces, which govern electricity, magnetism, and chemical reactions. Dark matter, however, does not show any of these behaviors. Telescopes cannot see it, and it does not produce radiation in any wavelength. If it were made of ordinary atoms, we would have detected it long ago using existing instruments. Its invisibility and lack of interaction with electromagnetic forces tell scientists that dark matter is something completely different from the familiar matter around us. Understanding this difference is key to unlocking the secrets of the universe. Normal atoms interact with light and electromagnetic forces in predictable ways. This interaction is why stars shine, gas glows, and planets reflect sunlight. It also allows telescopes and other instruments to detect ordinary matter across vast distances in space. Electromagnetic forces govern almost all interactions in our daily experience. They allow atoms to bond, form molecules, and create the visible universe. Dark matter does not participate in any of these processes. It does not form atoms, molecules, or the familiar structures we see around us. Its behavior is entirely different, governed mainly by gravity rather than the forces that control ordinary matter. This explains why it can form large halos and cosmic filaments without being visible. By studying what dark matter does not do, scientists learn about its unique properties and how it shapes the universe. Dark matter appears to interact primarily through gravity. Unlike normal matter, it does not produce light, experience friction, or form chemical bonds. Its influence is felt over vast distances through its gravitational pull, shaping the motion of stars, galaxies, and clusters. This makes it invisible but massive, silently holding galaxies together and guiding their formation. Dark matter also dominates the large-scale structure of the universe, forming the scaffolding on which galaxies and filaments appear. While we cannot see it or detect it directly with ordinary instruments, its gravitational effects provide a reliable way to study it. Observations of galaxy rotation, cluster dynamics, and gravitational lensing all confirm that dark matter exerts gravity like ordinary matter. Its mysterious nature lies in its lack of interaction with light or other forces, but its presence is undeniable. Gravity is its signature, and it is the tool scientists use to trace this invisible cosmic material. One of the leading ideas about what dark matter might be is the concept of weakly interacting massive particles, or WIMP. Scientists propose that these hypothetical particles are very different from normal matter. They would have mass, which allows them to exert gravity, but they barely interact with the matter we are familiar with. They do not emit or absorb light, and they do not respond to electromagnetic forces. WIMPs are predicted to make up most of the dark matter in the universe, forming the halos around galaxies and filaments of the cosmic web. Because they interact so weakly, they are incredibly difficult to detect. Researchers build sensitive detectors deep underground, shielded from cosmic rays and other interference, in the hope of capturing a rare interaction with a WIMP. Even though none have been detected yet, WIMPs remain one of the most studied and plausible candidates for dark matter. These hypothetical particles would barely interact with normal matter, making them almost invisible to everything we use to observe the universe. Unlike atoms or molecules, WIMPs do not collide with other particles in any noticeable way. They do not slow down when passing through gas, stars, or even solid objects. Their weak interaction means that they can move freely through space without being absorbed, scattered, or stopped. This property explains why dark matter can form enormous halos around galaxies without clumping like ordinary matter. It also accounts for the difficulty in detecting dark matter directly. Despite their near invisibility, WIMPs still have mass and respond to gravity, which is why their presence is observed indirectly through galaxy motion and gravitational lensing. Their elusive nature keeps scientists searching for clever ways to detect them. If WIMPs exist, they could pass through entire planets without leaving a trace. Unlike normal particles, which collide and interact with atoms in matter, WIMPs are so weakly interacting that they go through solid material almost as if it wasn't there. A WIMP could travel through Earth, through mountains, or even through the human body without ever being stopped or absorbed. This makes them extremely difficult to study, because almost all particles we detect in labs interact in some way with matter. Scientists must build experiments in underground labs, using huge amounts of shielding, to reduce background noise and have even the slightest chance of detecting a WIMP. The idea that particles can pass unnoticed through entire planets is astonishing, yet it is a key feature of many dark matter theories. It also shows how mysterious the universe can be. In fact, if WIMPs exist, trillions of them might pass through your body every second without you noticing. Our bodies, like Earth and everything else, are constantly immersed in a sea of dark matter. These particles move through space at high speeds, and because they barely interact with ordinary matter, they slip through atoms without any effect. This means that you are continuously bathed in invisible dark matter, yet it causes no harm. Even though trillions may pass through each of us every second, we remain completely unaware because they interact so weakly. It is a humbling thought, showing that most of the matter in the universe is completely invisible and indifferent to our presence. This also highlights why detecting dark matter is so challenging. Its existence is felt only through gravity and subtle indirect effects. Even though WIMPs could be passing through everything constantly, they remain almost impossible to detect. Their weak interactions with normal matter mean that they rarely collide with atoms, making detection extremely difficult. Ordinary detectors are overwhelmed by other particles, radiation, and cosmic rays, which can create signals that mimic what scientists are looking for. Because WIMPs interact so weakly, even the most sensitive instruments might not register a single particle for months or years. This elusiveness is part of what makes dark matter so mysterious. Scientists have had to think creatively, designing experiments that can spot the tiniest signals from a potential WIMP interaction, while eliminating interference. Even a single detection could confirm the existence of these elusive particles. The challenge is enormous, but the reward is equally huge: understanding what makes up most of the matter in the universe. To increase the chances of detecting dark matter, scientists have built specialized detectors deep underground. These detectors are placed in mines, tunnels, or other locations shielded by rock and earth. The underground location reduces interference from cosmic radiation and high-energy particles that constantly bombard Earth's surface. By minimizing background noise, these detectors can focus on the extremely rare events that might indicate a dark matter particle has interacted with normal matter. The detectors often contain large amounts of target material, such as liquid xenon, designed to capture tiny signals from WIMP-sensitive instruments, then measure flashes of light or electrical signals produced by these rare interactions. Underground laboratories allow scientists to create the quietest possible environment for these experiments, increasing the likelihood of catching evidence of dark matter. The reason these detectors are deep underground is to block cosmic radiation. At Earth's surface, particles from the sun and outer space constantly strike the atmosphere, producing secondary particles that can interfere with sensitive measurements. Underground locations provide a natural shield because the surrounding rock absorbs most of these particles. This drastically reduces the number of false signals in the detectors, making it possible to observe the rare and faint signs of dark matter. Shielding also protects the experiment from temperature fluctuations, vibrations, and electromagnetic interference. By creating such controlled conditions, scientists increase the chance of detecting a true interaction with a WIMP if it occurs. Even with these precautions, dark matter detection is extremely difficult, which is why these experiments require patience, precision, and massive target volumes. The underground environment is essential for making the invisible slightly less invisible. One of the most advanced experiments searching for dark matter is the Zwicky experiment. Located deep underground in the Sanford Underground Research Facility in South Dakota, USA, it uses a huge tank of liquid xenon to detect potential WIMP interactions. When a dark matter particle passes through, it might collide with a xenon atom, producing tiny flashes of light or a small electrical signal. Extremely sensitive sensors detect these signals, which are then analyzed to distinguish real events from background noise. Zwicky is one of the most powerful dark matter detectors in the world, combining advanced technology with massive shielding from cosmic radiation. Experiments like this represent the cutting edge of the search for dark matter, offering one of the best chances yet to directly observe particles that make up the invisible majority of the universe. Each test, measurement, and analysis brings scientists closer to solving one of the greatest mysteries of modern astronomy. These dark matter experiments focus on watching for extremely rare collisions between dark matter particles and ordinary atoms. Since WIMPs interact so weakly with matter, Such collisions happen only once in a long while. Detectors like LuxE-PLIN are designed to capture these tiny events, often producing flashes of light or electrical signals when a particle interacts with an atom in the target material. Scientists then analyze the data to separate potential dark matter signals from background noise caused by cosmic rays or natural radiation. Each event is studied carefully to determine if it could be caused by a WIMP. Because these interactions are so rare, experiments must run for months or even years to have a chance of seeing one. Despite these efforts, no confirmed detection has occurred yet, but the search continues. Every experiment narrows down the possibilities, helping scientists refine their theories and focus on where dark matter might be hiding. Patience and precision are key in this invisible hunt. So far, despite decades of searching and incredibly sensitive experiments, no confirmed detection of dark matter has occurred. Scientists have not yet directly observed a WIMP or any other proposed particle interacting with ordinary matter. This lack of direct evidence does not mean dark matter does not exist. It simply shows how elusive it is. Observations of galaxy motions, gravitational lensing, and the cosmic web all still point to the presence of dark matter. Researchers continue to design more sensitive detectors, try new materials, and develop innovative methods to detect it. The absence of confirmed detection keeps scientists exploring alternative possibilities, such as particles lighter than WIMPs or particles that interact in unexpected ways. Every negative result helps narrow down the characteristics dark matter can have, guiding future experiments. Even without a direct observation, the gravitational effects of dark matter remain undeniable, making it one of the most mysterious components of the universe that we are determined to understand. Another idea is that dark matter might not be made of heavy particles like WIMPs, but instead consist of extremely light particles. These particles would be much smaller than atoms, even lighter than electrons, and could behave in very different ways from WIMPs. Because of their tiny mass, they could spread out across space and create smooth distributions rather than clumping like heavier particles. Their interactions with ordinary matter would be even weaker, making them extraordinarily difficult to detect. Scientists theorize that these light particles could also contribute to the gravitational effects we attribute to dark matter. Detecting them might require completely different methods than those used for WIMPs. The idea that dark matter could be made of such tiny, invisible particles opens up new avenues for research and experimentation, showing that the universe might be stranger than we can currently imagine. One possible candidate for these extremely light dark matter particles is called the axion. Axions are hypothetical particles proposed by physicists to solve certain problems in particle physics and cosmology. They would be nearly massless and would barely interact with ordinary matter, similar to WIMPs but on a much smaller scale. Axions could form a background field across the universe, influencing the motion of stars and galaxies through gravity. Because of their small mass, trillions of axions could pass through your body every second without you noticing. Scientists are now building specialized detectors, such as resonant cavities and magnetic field experiments, designed to pick up tiny signals from axions. Detecting axions would not only confirm a candidate for dark matter, but also answer deep questions about fundamental physics. Like WIMPs, axions remain theoretical for now, but they represent one of the most promising paths for solving the mystery of what dark matter is made of. Axions are unusual because they would behave more like waves than traditional particles. Unlike heavier particles that move like tiny billiard balls, axions could spread out over large regions of space, forming smooth, wave-like patterns. This property could explain why dark matter appears so evenly distributed in some areas while still forming halos around galaxies. Their wave-like behavior makes detecting them very challenging because they do not collide with ordinary matter in the way heavier particles do. Instead, scientists have to look for tiny, subtle effects these waves might produce, such as very weak electromagnetic signals. Understanding axions requires combining knowledge from particle physics and cosmology, as they are so different from the matter we experience in daily life. Their wave-like nature is one of the reasons dark matter is so mysterious. It shows that the universe may be governed by behaviors very unlike anything we see on Earth, where matter usually acts like solid particles. Experiments searching for axions are extremely delicate because the signals they might produce are incredibly faint. Scientists use highly sensitive instruments such as resonant cavities, strong magnetic fields, and superconducting detectors to try to pick up these tiny effects. The idea is that axions passing through a magnetic field could convert into very weak photons, creating detectable flashes of energy. These signals are rare and tiny, so experiments must be carefully shielded from background noise and interference. Even a single detection would be revolutionary, providing evidence for one of the most mysterious components of the universe. Researchers also analyze large amounts of data to separate possible axion signals from other sources. The search is ongoing, and each experiment, whether successful or not, helps refine our understanding of where and how to look for dark matter. Detecting axions would open a new chapter in understanding the invisible universe. Some theories suggest that dark matter formed just moments after the Big Bang, during the earliest moments of the universe's existence. As the universe expanded and cooled, normal matter formed atoms, while dark matter already existed in a stable form. Because it does not interact with light or electromagnetic forces, it could clump under gravity and begin forming the cosmic scaffolding, before ordinary matter even had a chance to condense into stars and galaxies. This early formation explains why dark matter dominates the mass of the universe and guides the formation of large-scale structures. Studying the early universe through cosmic microwave background radiation and other signals gives scientists clues about how dark matter behaved in those first moments. These theories show that dark matter is not a recent addition, but a fundamental part of the universe from the very beginning. Its presence has been shaping cosmic evolution since time itself started. If dark matter formed so early, it means it has existed for nearly the entire history of the universe. Billions of years before the first stars lit up, dark matter was already influencing the cosmos. Its gravity shaped the growth of galaxies and clusters, and it continues to hold structures together today. This longevity makes dark matter different from most forms of ordinary matter, which change, interact, and recycle over time. Dark matter has remained largely stable, silent, and invisible, quietly guiding the motion of galaxies and maintaining the cosmic web. Its presence across nearly 14 billion years highlights its importance in the evolution of the universe. Studying it gives scientists insight not only into the invisible components of space, but also into the history and origins of everything we see. Dark matter is like a hidden thread that has been weaving the universe together from the very beginning. From the very beginning, dark matter has had a profound impact on cosmic evolution. As the universe expanded after the Big Bang, dark matter's gravity helped organize matter into structures. It guided gas and dust into the regions where galaxies would eventually form, shaping the cosmic web of filaments and clusters. Without dark matter, matter would have remained nearly uniform, and large-scale structures like galaxies and galaxy clusters might never have emerged. Its influence continued over billions of years, affecting star formation, galaxy mergers, and the overall organization of the cosmos. Even today, dark matter continues to affect the motions of stars and galaxies. By studying its effects, scientists can learn how the universe grew from a nearly featureless cloud of particles into the complex and structured system we observe today. Dark matter is not just a background presence. It is an active participant in shaping the universe from the very start, silently guiding the evolution of cosmic structures. Dark matter might even play a role in determining the long-term fate of galaxies. Because it dominates the mass in most galaxies, its gravitational pull affects how stars and gas move and remain bound. Without enough dark matter, galaxies could gradually disperse, losing stars to intergalactic space. Its presence ensures that galaxies stay stable over billions of years, maintaining their shapes and preventing them from tearing apart. In some cases, dark matter may influence galaxy collisions and mergers, determining how galaxies grow and evolve over time. Studying these effects helps astronomers predict the future behavior of galaxies, including our own Milky Way. Dark matter's role in long-term galaxy dynamics highlights its importance beyond just forming the cosmic web. It continues to shape the destiny of galaxies. Its invisible hand guides the structure, motion, and evolution of the universe on timescales far longer than human experience. Some galaxies are almost entirely dominated by dark matter. In these galaxies, ordinary matter like stars and gas makes up only a small fraction of the total mass. Their visible components are tiny compared to the massive halo of dark matter surrounding them. These galaxies rotate in ways that cannot be explained by the stars and gas alone, revealing that dark matter provides most of their gravitational pull. Studying these galaxies is particularly interesting because they allow scientists to observe the effects of dark matter without much interference from ordinary matter. Their existence confirms that dark matter can dominate the structure and behavior of an entire galaxy. It also challenges our understanding of galaxy formation, showing that some systems can exist almost entirely in the shadow of the invisible mass that governs their motion and evolution. These galaxies, dominated by dark matter, are often small and faint, earning them the name dark matter-dominated dwarf galaxies. They are much smaller than typical spiral or elliptical galaxies, with relatively few stars, yet they are rich in dark matter. Their motions and internal dynamics are controlled almost entirely by the gravitational pull of dark matter. Dwarf galaxies provide astronomers with natural laboratories to study dark matter, because the visible matter contributes very little to the overall mass. Observations of these galaxies help refine models of dark matter distribution, particle properties, and its role in cosmic structure formation. Despite their small size and faint appearance, dark matter-dominated dwarf galaxies are crucial for understanding the invisible majority of the universe. They highlight how dark matter can govern entire systems, shaping even the tiniest galaxies in profound ways. In some dark matter-dominated dwarf galaxies, the number of stars is astonishingly low. These galaxies may contain only a few thousand stars, compared to the hundreds of billions in galaxies like the Milky Way. Despite their tiny population of visible stars, their motions reveal something extraordinary. The stars orbit as if they are moving inside a much larger gravitational field. This indicates that the mass of the galaxy is overwhelmingly made up of invisible dark matter. The stars are essentially tracing the shape and strength of the surrounding dark matter halo. Studying these galaxies allows scientists to isolate the effects of dark matter without the complexity introduced by large amounts of ordinary matter. These faint galaxies act as natural laboratories, showing clearly that most of the universe's mass is invisible. Even with very few stars, the galaxy's dynamics cannot be explained without invoking enormous amounts of dark matter, highlighting how dominant and influential this invisible mass truly is. Yet, despite having very few stars, these galaxies behave as if enormous mass surrounds them. The stars move in patterns that can only be explained if the galaxy is embedded in a massive dark matter halo. Their rotation speeds are much higher than what the visible matter alone could produce, and their structure remains stable over billions of years. This invisible mass dominates the gravitational pull, keeping the galaxy intact. By measuring how stars orbit within these faint galaxies, astronomers can map the dark matter distribution and estimate its total amount. It is remarkable to realize that galaxies with almost no visible matter can still have a strong gravitational presence. These observations confirm that dark matter is not just a minor component of the universe. It controls the behavior and stability of entire galaxies, even the smallest and faintest ones. The invisible dominates the visible in surprising ways. On the other hand, some galaxies appear to contain very little dark matter. These rare galaxies are exceptions to the usual pattern where dark matter dominates. In these systems, the motion of stars can be explained mostly by the visible matter, such as stars and gas, without invoking a large halo of dark matter. Observations of these galaxies have puzzled astronomers because they challenge our understanding of galaxy formation. If dark matter is everywhere and forms the scaffolding for cosmic structures, why do some galaxies seem to lack it? These discoveries suggest that galaxy formation is more complex than previously thought, and that processes such as galaxy collisions, tidal interactions, or other mechanisms might strip away dark matter in certain cases. Studying these unusual galaxies provides important clues about how dark matter behaves and interacts with ordinary matter across cosmic history. These rare discoveries challenge current theories about dark matter and galaxy formation. They suggest that the distribution of dark matter is not uniform, and that some galaxies can exist with almost no dark matter at all. This raises questions about how dark matter interacts with ordinary matter, and how it can be removed or redistributed during a galaxy's evolution. The existence of dark matter-poor galaxies forces scientists to refine their models and consider alternative scenarios, such as environmental effects or unusual formation histories. These galaxies provide critical tests for our understanding of cosmology and the role of dark matter in shaping the universe. Each new observation of a galaxy with little or no dark matter challenges the assumption that dark matter is always dominant and prompts researchers to think differently about its influence. These findings make the study of dark matter even more fascinating and unpredictable. Scientists continue debating how galaxies with very little dark matter could exist. These galaxies challenge the long-held idea that dark matter is the main ingredient in forming and holding galaxies together. Some researchers suggest that interactions with other galaxies or strong gravitational forces could strip dark matter away. Others propose that unusual formation histories might produce galaxies naturally low in dark matter. Observing these galaxies helps scientists test different theories about how dark matter behaves and interacts with visible matter. Each new discovery adds complexity to our understanding of the universe, showing that dark matter's role is not always simple or uniform. The debate continues because current models cannot easily explain these anomalies. Studying these exceptions forces astronomers to think critically about the mechanisms behind galaxy formation, the behavior of dark matter, and the conditions that can create such unusual cosmic systems. The mystery keeps researchers searching for explanations. Another strange observation that highlights the unusual behavior of dark matter involves galaxy collisions. When galaxies collide, their stars usually pass by each other with little effect because the distances between stars are vast. However, the gas and dust clouds interact strongly, slowing down due to friction and heating up, creating bright X-ray emissions. By studying these collisions, scientists can observe how different components, stars, gas, and dark matter, behave differently under extreme conditions. These observations provide unique insights into the invisible nature of dark matter. Unlike gas and dust, dark matter does not interact electromagnetically, meaning it does not slow down during collisions. Observing galaxy collisions allows astronomers to separate the effects of dark matter from ordinary matter and confirm its presence in the universe. These events act as natural laboratories for testing dark matter theories. One of the most famous examples of a galaxy collision is the bullet cluster. This system consists of two galaxy clusters that collided at incredibly high speeds. Astronomers have studied it extensively using X-ray telescopes and gravitational lensing. The X-ray images reveal the hot gas that makes up most of the ordinary matter in the clusters, while lensing maps show where the mass is concentrated. Remarkably, the majority of the mass, revealed by lensing, does not coincide with the hot gas. Instead, it is located in regions where little ordinary matter exists, providing clear evidence for dark matter. The bullet cluster serves as one of the most direct observations of dark matter, showing that it behaves differently from ordinary matter during cosmic collisions. It is a striking example of how gravity reveals the unseen. In the bullet cluster collision, normal matter slowed down due to friction and interaction, while dark matter passed through almost unaffected. The gas clouds collided, heated up, and emitted X-rays, but the dark matter did not interact with itself or the gas in the same way. Gravitational lensing showed that the bulk of the mass remained ahead of the gas clouds, tracing where the dark matter went. This separation between visible and invisible matter confirmed that dark matter responds primarily to gravity, not electromagnetic forces. Observing this behavior helps scientists understand the properties of dark matter, such as how weakly it interacts with ordinary matter and with itself. The bullet cluster provides one of the clearest cosmic experiments, showing that dark matter exists and behaves in ways entirely different from the matter we can see. It is a natural demonstration of dark matter's mysterious yet powerful role in shaping the universe. The separation observed in the bullet cluster provided one of the strongest pieces of evidence for dark matter. By comparing X-ray images of hot gas with gravitational lensing maps, astronomers saw that most of the mass did not coincide with the ordinary matter. The visible gas slowed down, while the majority of the mass, attributed to dark matter, moved ahead almost untouched. This clear difference between what we can see and what we can measure gravitationally left little doubt that a large amount of invisible matter exists. Unlike stars or gas, which interact through collisions and electromagnetic forces, dark matter behaves differently. The bullet cluster acted as a natural experiment in the universe, showing that invisible mass dominates the gravitational landscape. It remains one of the most visually compelling and scientifically persuasive pieces of evidence for dark matter, directly confirming its presence beyond indirect measurements like galaxy rotation curves or simulations. The bullet cluster also demonstrated that dark matter behaves very differently from normal gas and stars. While stars mostly pass through the collision without colliding, the gas clouds experienced friction, heating up and slowing down. Dark matter, however, seemed almost completely unaffected by the collision. It did not collide, emit radiation, or form shocks like the gas. Instead, it stayed aligned with the galaxy cluster's overall gravitational centers. This behavior confirms that dark matter interacts primarily through gravity, and not through the electromagnetic forces that dominate ordinary matter. Observing this difference helps scientists understand why dark matter forms the invisible scaffolding that holds galaxies and clusters together. Unlike normal matter, it can pass through dense regions without being slowed or absorbed, which is crucial for the large-scale structure of the universe. Dark matter barely interacts even with itself, another remarkable property revealed by collisions like the bullet cluster. Unlike gas, which collides and slows down, or stars, which can scatter under strong forces, dark matter passes through both ordinary matter and other dark matter almost unaffected. This weak self-interaction allows dark matter to form smooth, extended halos around galaxies without clumping too tightly or fragmenting. It also explains why dark matter can dominate large-scale structures while remaining invisible and diffuse. Scientists use these observations to place limits on how strongly dark matter particles might interact with each other. Understanding this property is essential for simulations and theories, as it influences how galaxies, clusters, and filaments form and evolve. The near absence of self-interaction is one of the defining characteristics that makes dark matter so different from any matter we are familiar with. This very weak interaction with itself helps explain how cosmic structures form so smoothly. Dark matter does not get tangled, clump excessively, or collide in ways that disrupt galaxies or filaments. Its gravitational influence guides ordinary matter into patterns that create the large-scale cosmic web observed today. Because dark matter can move freely without colliding, it forms stable halos that support galaxy formation and maintain the structure of clusters over billions of years. This smooth behavior is essential for understanding why galaxies have such well-defined rotation curves, and why the universe shows a consistent, organized structure at the largest scales. By acting as a stable framework, dark matter allows stars, gas, and galaxies to settle into predictable formations. Its silent, invisible hand shapes the universe continuously, creating a cosmos that appears orderly even though most of its mass is hidden from view. Some theories suggest that dark matter may interact through forces that we have not yet discovered. Unlike the forces we know, gravity, electromagnetism, and the strong and weak nuclear forces, these hypothetical interactions could operate entirely in the invisible part of the universe. If such forces exist, they might explain some of the unusual behaviors of dark matter that cannot be accounted for by gravity alone. Scientists are exploring models that include these hidden interactions, but so far there is no direct evidence. Detecting them would require completely new types of experiments, designed to look for subtle effects in particle behavior or in the motions of galaxies. These unknown forces could be very weak or operate only under specific conditions, which is why dark matter has remained so elusive. The idea that dark matter could interact in unknown ways expands the possibilities for understanding this invisible substance and opens exciting directions for future research in fundamental physics. If these hypothetical interactions exist, it could mean there is an entire hidden dark sector of physics that we have never observed. Just as ordinary matter has particles, forces, and complex interactions, the dark sector might have its own structure, complete with dark particles and dark forces. This sector would operate largely independently from the ordinary matter we experience, except through gravity or perhaps other very weak interactions. Scientists speculate that the dark sector could contain phenomena similar to our universe, but invisible and undetectable with current instruments. It might include dark matter particles that interact with each other, dark radiation, or even dark equivalents of atoms and molecules. Exploring the possibility of a dark sector could revolutionize our understanding of the cosmos, showing that the visible universe is only a small part of a much larger hidden system. While purely theoretical at this stage, it represents one of the most intriguing frontiers in modern physics. Within this hidden dark sector, some theories suggest the existence of dark atoms or dark radiation. Dark atoms would be formed by hypothetical dark particles that bind together, similar to how protons and electrons form normal atoms. Dark radiation could carry energy across the dark sector, much like photons carry energy in the visible universe. These components would be invisible to ordinary instruments, but could influence the universe's evolution through gravity or subtle effects on galaxy formation. If they exist, they would represent a completely new form of matter and energy, operating alongside the familiar universe. Detecting such entities would require innovative methods that go beyond conventional particle physics and astronomy. The possibility of dark atoms and dark radiation expands the imagination of scientists, suggesting that there might be hidden complexity in the universe far beyond what we can see. Despite the exciting possibilities, all ideas about dark forces, dark atoms, and dark radiation remain purely theoretical. No experiment has yet confirmed the existence of a dark sector or any interactions beyond gravity. These theories are based on mathematical models and indirect observations, guided by the need to explain dark matter's behavior. Scientists use these models to make predictions, design experiments, and search for subtle signals that could confirm the existence of a hidden world. Until direct evidence is found, these ideas remain speculative but scientifically valuable. They push the boundaries of what we know about the universe, reminding us that most of the cosmos may be invisible and governed by rules we do not yet understand. The exploration of a possible dark sector represents both a challenge and an opportunity to expand our understanding of the fundamental nature of reality. The search for dark matter is one of the biggest challenges in modern physics. Scientists have been trying to understand this invisible substance for nearly a century, yet it remains elusive. Its presence is felt only through gravity, and it does not emit, absorb, or reflect light, making direct detection extremely difficult. Researchers around the world are designing experiments, building sensitive detectors, and studying galaxies to uncover its properties. Understanding dark matter is essential not only for explaining the motions of galaxies and the structure of the universe, but also for answering fundamental questions about the nature of matter itself. Every observation, simulation, and experiment adds pieces to the puzzle, gradually narrowing down the possibilities. The mystery of dark matter continues to drive scientists to explore new theories, push technological boundaries, and rethink the rules of physics. It represents one of the most profound unknowns in our understanding of the cosmos. To solve this mystery, massive observatories, particle accelerators, and space telescopes are all involved in the search for dark matter. Observatories on Earth and in space monitor galaxies, clusters, and cosmic radiation to map dark matter's influence on visible matter. Particle accelerators, like the Large Hadron Collider, collide particles at extremely high energies to see if dark matter particles can be created or detected indirectly. Space telescopes can observe gravitational lensing and cosmic microwave background signals, offering insights into how dark matter shaped the universe. This multi-pronged approach is necessary because dark matter is invisible and interacts so weakly with ordinary matter. By combining astronomical observations with high-energy physics experiments, scientists aim to find the first direct evidence of dark matter particles. Each method provides complementary information, helping researchers approach the mystery from multiple angles. Even the Large Hadron Collider plays a role in the search for dark matter. By smashing protons together at nearly the speed of light, it recreates conditions similar to those just after the Big Bang. In these high-energy collisions, scientists hope that dark matter particles, if they exist, could be produced for a brief moment. These particles would escape the detectors without interacting, but their presence could be inferred from missing energy or momentum in the collision results. Observing such events would be groundbreaking, providing direct evidence of particles that make up most of the universe's mass. The LHC experiments also test theories about dark matter interactions, WIMPs, and other hypothetical particles, helping to narrow the possible properties of dark matter. Even without a direct detection yet, the collider provides critical constraints that guide future experiments. Scientists hope that collisions at high energy might create dark matter particles temporarily, giving them a chance to study these elusive entities. By analyzing the products of particle collisions, researchers look for signs that energy has gone missing, which could indicate that invisible particles were produced. These fleeting events could reveal the mass, properties, and behavior of dark matter. Even a tiny signal would have enormous implications, confirming a particle candidate and opening a window into the invisible universe. High-energy collisions allow scientists to probe the fundamental laws of nature in ways that cannot be achieved through observation alone. Each experiment, whether successful or not, refines our understanding of what dark matter could be and how it interacts. The hope of creating and detecting dark matter in the lab keeps physicists pushing the limits of technology and imagination, seeking answers to one of the greatest mysteries of the universe. If dark matter is finally discovered, it would revolutionize our understanding of the universe. For nearly a century, scientists have known that most of the matter in the cosmos is invisible, but its exact nature remains unknown. Finding a particle or some other form of dark matter would answer countless questions about galaxy formation, cosmic evolution, and the fundamental laws of physics. It could explain why galaxies rotate the way they do, why galaxy clusters hold together, and why the cosmic web forms the structures we see today. Beyond astronomy, a discovery could also impact particle physics, revealing new particles or forces that were previously unknown. It would open entirely new fields of research, guiding scientists to explore both the visible and invisible universe in unprecedented ways. The impact would be profound, altering textbooks, experiments, and our understanding of reality itself. Dark matter's discovery would be one of the most significant breakthroughs in human history. Yet, there is also a possibility that our theory of gravity may need revision. Some scientists suggest that instead of adding invisible matter to explain galaxy motions, the laws of gravity might behave differently on cosmic scales. Known theories, like Newtonian gravity or general relativity, work extremely well in the solar system, but may not fully explain the motions of galaxies and clusters without dark matter. If gravity works differently over very large distances, the missing mass problem might be solved without invoking an invisible substance. This idea is controversial because it challenges centuries of established physics. Revising gravity would require new equations and a completely different understanding of how matter interacts over space. Researchers explore these possibilities through careful observations of galaxies, clusters, and cosmic phenomena, looking for subtle deviations from expected gravitational behavior. While intriguing, These alternative theories face significant hurdles in explaining all the evidence that supports dark matter. Some physicists explore alternatives that modify gravity instead of adding dark matter. These modified gravity theories propose changes to the way gravity works at large distances or low accelerations. One famous example is MOND, which stands for Modified Newtonian Dynamics. According to MOND, the force of gravity changes slightly when dealing with very small accelerations, like those in the outer regions of galaxies. These theories attempt to explain galaxy rotation curves, cluster dynamics, and gravitational lensing without invoking invisible matter. While modified gravity can match some observations, it struggles to explain others, such as the bullet cluster, where dark matter and ordinary matter separate clearly. Scientists continue to test these ideas by comparing predictions with observations from telescopes, space missions, and simulations. Exploring alternative theories helps ensure that the search for dark matter is thorough and challenges assumptions, keeping the scientific process honest and open to new possibilities. However, most current observations still strongly support dark matter as the main explanation for the universe's missing mass. From galaxy rotation curves to the cosmic microwave background, from gravitational lensing to the structure of galaxy clusters, evidence consistently points to invisible matter dominating the cosmos. Collisions like the bullet cluster clearly show that mass exists where we cannot see ordinary matter. Simulations that include dark matter accurately reproduce the large-scale structure of the universe, while models without it fail to match observations. While alternative gravity theories offer interesting possibilities, they have yet to explain all phenomena as consistently as dark matter does. This overwhelming body of evidence makes dark matter the leading theory in modern astrophysics. Scientists continue to investigate, but for now, the universe seems to be filled with a mysterious, invisible mass that silently governs the motion of galaxies, shapes cosmic structures, and holds the key to understanding everything around us. This means that the universe may be mostly made of something we cannot see. While stars, planets, and gas clouds make up the parts of the cosmos we can observe, they account for only a small fraction of the total matter. The rest, about 85%, is dark matter, invisible to telescopes and undetectable through ordinary means. It does not shine, reflect, or absorb light, yet its gravitational pull dominates the motion of galaxies, galaxy clusters, and even the large-scale structure of the universe. In essence, everything we see is floating within a much larger invisible framework. This challenges our everyday understanding of reality, because most of the mass in the universe exists in a form completely unlike the matter we know. Scientists continue to study this invisible majority, using gravity as the only clue to its presence. Dark matter may hold answers to some of the most fundamental questions about the origin, evolution, and ultimate fate of the universe. Every galaxy, including our own, floats inside an enormous dark matter halo. These halos extend far beyond the visible edges of galaxies, often hundreds of thousands of light-years across. The stars, gas, and planets that we see are only the tip of the iceberg. The invisible halo provides most of the gravitational glue that keeps everything together. Without these halos, galaxies would not rotate as observed, and they could even tear themselves apart over time. Observations of other galaxies show similar halos everywhere, suggesting that this invisible structure is a universal feature. Our Milky Way, too, is embedded in such a halo, which defines the shape, size, and motion of our galaxy. By studying these halos, astronomers can map how dark matter is distributed and how it affects the formation of stars, planetary systems, and galactic evolution. Dark matter halos are the hidden scaffolding of the universe, surrounding and supporting every galaxy. Right now, invisible matter surrounds our entire solar system. Even as the Sun and planets orbit the center of the Milky Way, they are embedded within the Milky Way's massive dark matter halo. This means that trillions of invisible particles flow through and around us constantly, though we cannot see or feel them. The solar system's gravity interacts mainly with the Sun and planets, but on larger scales, dark matter's gravity contributes to the overall motion of stars and systems in the galaxy. Understanding the local density of dark matter is important for experiments that try to detect it directly on Earth. Even though it is invisible, its presence is real, shaping the environment of our galaxy and influencing how stars, gas, and planets move over billions of years. In a very real sense, we live inside a vast, unseen ocean of matter that dominates the galaxy. And as we slowly move through the Milky Way, we are quietly passing through this unseen ocean of dark matter. Every motion of the Earth, the solar system, and the galaxy itself carries us through a sea of invisible particles. They exert gravitational influence on our galaxy, guiding the orbits of stars and the structure of the Milky Way over billions of years. While we remain unaware of it in daily life, dark matter surrounds us at every moment, a silent and invisible companion shaping the universe. This constant presence reminds us that most of reality exists beyond what our senses and instruments can directly perceive. It also means that the universe is more mysterious and complex than we can imagine, dominated by invisible forces and matter that hold everything in place. Dark matter quietly defines the cosmic stage on which all visible matter performs.